Hello, chemistry students. Dr. Tullis here. In this section, you will understand the chemistry and advantages and disadvantages of dry cells, alkaline batteries, lead storage batteries, lithium batteries, and nickel-cadmium batteries. You will understand how fuel cells work and recognize the difference between batteries and fuel cells. The cells described so far are unlikely to have practical use. They are neither compact nor robust. Commercial voltaic cells provide energy for a wide range of devices, come in a large variety of sizes and shapes, and produce different voltages. Some are rechargeable, others are discarded after use. In most situations, it's also important that the cell produce a constant voltage, even while current is drawn from the cell. And the problem with the cells described so far is that the voltage produced varies as the concentrations of reactants and products change. Drawing a current results in a decrease in the voltage if reactant concentrations near the anode or the cathode are depleted faster than they can be replenished from the bulk of the solution. Similarly, a decrease in voltage occurs if product concentrations increase near the electrodes faster than they move into the bulk solution. One might think that there is nothing further to learn about batteries, but that's not true. Research on these devices is actively pursued in the chemical community. The electrical work that can be drawn from a voltaic cell depends on the quantity of reagents consumed. A voltaic cell must have a large mass of reactants to produce current over a prolonged period. Additionally, a voltaic cell that can be recharged is very attractive. Recharging a cell means returning the reagents to their original sites in the cell. In many types of electrochemical cells, the movement of ions in the cell mixes the reagents, and they cannot be unmixed after the cell has been running. Batteries can be classified as primary or secondary. Primary batteries cannot be returned to their original state by recharging. So when the reactants are consumed, the battery goes dead, and it must be thrown away. Secondary batteries are often called storage batteries or rechargeable batteries. The reactions in these batteries can be reversed, so the batteries can be recharged. There's been years of development that have led to many different commercial voltaic cells to meet different needs. Several common ones are going to be described. All adhere to the principles that have been developed in earlier discussions. The first one we're going to look at is the dry cell battery. If you were to buy a cheap flashlight battery or a dry cell battery, it might be a modern version of a voltaic cell. Zinc serves as the anode, and the cathode is a graphite rod right here that is placed down the center of the device. These cells are often called dry cells because there's no visible liquid phase. However, the cell does contain a moist paste of ammonium chloride, zinc chloride, or manganese dioxide. Here we can see this paste. So because of that, water is present. That moisture is necessary because the ions present must be able to migrate between the carbon cathode and the zinc anode. The cell generates a potential of about 1.5 volts using these two half reactions. Notice that the products of the cathode are gases, which can build up pressure in the cell and cause it to rupture. The problem is avoided, however, by two other reactions that take place in the cell. Ammonia binds to the zinc plus 2 ions, and hydrogen gas is oxidized by that manganese dioxide to water. These zinc carbon dry cells are widely used because they're pretty cheap, but there's lots of disadvantages. If current is drawn from the battery rapidly, the gas products cannot be consumed rapidly enough, so the cell resistance rises and the voltage drops. Also, the zinc electrode here and the ammonium ions are in contact in the cell, and those chemicals react slowly. Because of this reaction, these voltaic cells cannot be stored indefinitely, which you may have learned from experience. When the zinc outer shell deteriorates, the contents of the battery can leak and possibly damage the appliance with which it was stored in. If you've ever gone to change a battery and you've seen it corroded, that's what it would look like. Today, you're much more likely to use alkaline batteries in your camera or flashlight because they generate current up to 50% longer than a dry cell of the same size. The chemistry of alkaline cells is similar to that of the zinc carbon dry cell, except that the material inside the cell is basic or alkaline. Alkaline cells also use the oxidation of zinc and the reduction of the manganese dioxide to generate a current. But sodium hydroxide or potassium hydroxide is used in the cell instead of that acidic salt, that ammonium chloride from the previous slide. Alkaline cells, which produce about 1.5 volts, which is about the same as the dry cell, have the further advantage that the cell potential does not decline under high current loads because no gases are formed. Up here we have button batteries, also known as coin batteries, and they're used in small devices like watches, hearing aids, and key fobs for cars. Two common examples of button batteries are silver oxide batteries and zinc oxygen batteries. Both also operate under alkaline conditions, and both have zinc anodes. Moving on to secondary or rechargeable batteries. When a zinc carbon dry cell or an alkaline cell ceases to produce a usable electric current, it's often thrown away. In contrast, some types of cells can be recharged, often hundreds of times. Recharging requires applying an electric current from an external source to restore the cell to its original state. There are a number of well-known types of secondary batteries in common use. Let's look at the lead storage battery. An automobile battery, which is an example of a lead storage battery, is probably the best known rechargeable battery. The 12-volt version has 6 voltaic cells, and it can produce a large initial current, which is an essential feature when starting an automobile engine. Looking at this picture here, the anode of a lead storage battery is metallic lead. The cathode is also made of lead, but it's covered with a layer of compressed, insoluble lead-4 oxide, this PbO2. Then we can see these positive plates and these negative plates, those electrodes, are arranged alternately in a stack, and then they're separated by thin fiberglass sheets, and it's all immersed into sulfuric acid. When the cell supplies electrical energy, the lead anode is oxidized to insoluble lead-2 sulfate that adheres to the electrode surface. The 2 electrons that are produced per each lead atom move through the circuit to the cathode, where that lead-4 oxide is reduced to Pb2 plus ions, and so in the net ionic equation forms lead-2 sulfate. Here are the 2 half reactions. The anode is metallic lead, and our cathode is that lead-4 oxide, and we can see with these half reactions when the cell supplies electrical energy, that lead anode is oxidized to insoluble lead-2 sulfate that adheres to that electrode surface. The 2 electrons that's produced per lead atom moves through that circuit to the cathode, where the PbO2 is reduced. We can see it went from +4 to +2 to also form the PbSO4 insoluble lead-2 sulfate. When the current is generated, sulfuric acid right here is consumed and water is formed. And because water is less dense than sulfuric acid, the density of the solution decreases during this process. So one way to determine whether a lead storage battery needs to be recharged is to measure the density of the solution. When that lead storage battery is recharged by supplying electrical energy, that lead sulfate that's coating the surfaces of the electrodes is converted back to metallic lead and the PbO2, and the sulfuric acid is regenerated. Recharging this battery is possible because the reactants and products remain attached to the electrode surface. The lifetime of a lead storage battery, however, is limited because the coatings, the PbO2 and the PbSO4, will flake off of the surface over time, and it will fall to the bottom of that battery case. Scientists and engineers would like to find an alternative to lead storage batteries, especially for using in cars. Lead storage batteries have the disadvantages that they're really large and they're heavy, and lead and its compounds are toxic, making disposal pretty complicated. But the advantages of lead storage batteries, like its high current density and its long-term stability, often can outweigh those disadvantages. Then we have nickel-cadmium batteries that are used in a variety of cordless appliances like phones, camcorders, cordless power drills, and they're lightweight and rechargeable. The chemistry of the cell is based on the oxidation of cadmium, we can see here, Notice oxidation is the anode, so we have the oxidation of cadmium and the reduction of the nickel 3 oxide under basic conditions. Basic conditions we know as our hydroxide. As with the lead storage battery, the reactants and products formed when producing a current are solids that adhere to the electrodes. We can see here that our products are solids that adhere to those. The nickel-cadmium batteries produce a nearly constant voltage, about 1.2 volts, but the cost is pretty high, and there are restrictions on their disposal because cadmium compounds are toxic and are an environmental hazard. Then we have lithium batteries. Lithium-ion batteries are now commonly used to power devices from small electronics to electric vehicles. There's two types in common use, lithium-ion and a variant called lithium-ion polymer batteries. The chemistry of both is the same. Lithium is oxidized at the anode on the left. At the cathode, cobalt-4 oxide undergoes a 1 electron reduction, producing LiCoO2. The battery generates about 3.6 volt potential. An important reason for the development of lithium-based batteries is their lightweight. Lithium has a much lower molar mass. If you looked at the periodic table, it's 6.94 grams per mole, compared to cadmium, which is at 112, nickel about 59, or lead, which is 207. The oxidation of 7 grams of lithium produces the same number of electrons as the oxidation of 104 grams of lead. It's important not only in portable devices where people don't want to carry around heavy objects, but also in the automobile and the aircraft industry. Having a lighter weight battery in a car or airplane means more of the energy is going into moving the vehicle and less is being used to simply transport the battery. But even though they're popular, lithium-ion batteries are not perfect. If there was problems in the manufacturing or if there was any damage to the battery, there could be some violent reactions. Researchers are working to improve the safety of lithium-ion batteries by making changes to the anode, the cathode, or the electrolyte. An advantage of voltaic cells is that they're small and portable. But their size is also a limitation. The amount of electric current produced is limited by the quantity of reactants contained in the cell. When one of the reactants is completely consumed, the cell will no longer generate a current. Fuel cells avoid this limitation because the reactants, the fuel and the oxidant, can be supplied continuously to the cell from an external reservoir. Although the first fuel cells were constructed more than 150 years ago, little was done to develop this technology until the space program rekindled interest. Hydrogen-oxygen fuel cells have been used in NASA's Gemini, Apollo, and Space Shuttle programs. Not only are they lightweight and efficient, but they also have the added benefit that they generate drinking water for the ship's crew. Looking up here at the anode and the cathode, in a hydrogen-oxygen fuel cell, hydrogen is pumped into the anode of the cell, and oxygen is directed to the cathode where the following reaction occurs. The two halves, the cathode and the anode, are separated by a special material called a proton exchange membrane, or PEM. Protons, the H+, formed at the anode, right here, those H+, traverse or go across this proton exchange membrane and react with the hydroxide ions that are produced at the cathode, forming water. So the net reaction in the cell is the formation of water from H2 and O2, and it generates about 0.9 volts. Hydrogen-oxygen fuel cells operate at about 40 to 60% efficiency and meet most of the requirements for use in automobiles. They operate at room temperature or slightly above, they start rapidly, and they develop a high current density. But cost is a serious problem, as is the absence of an economical carbon-free way of making hydrogen. These faults and the cost and difficulty of building a nationwide infrastructure for distributed hydrogen remain major stumbling blocks that would need to be overcome before hydrogen fuel cells could be adopted for widespread use in automobiles. And here is a fun little diagram showing the energy of 1 kilogram of hydrogen is equal to the energy in 1 gallon of gasoline. For hydrogen, 1 kilogram of hydrogen can get you about 60 miles, and 1 gallon of gas can get you about 25 miles.